6 years ago. And so it did me the favor to present his work, which many of you know already. So yeah, let's just start. Thank you.
Thank you, Christian. So what I prepared is something very unusual for me, namely a very short talk with a very, very long question time. And so in order to organize a talk of this kind, especially in this situation, I decide to have some set of links to some questions that you can ask different questions, but we can use this set of links to go to bunches of transparencies. So let's start from the strong motivation of this talk, which I want to convert from materialist to informationalist, but it seems that you are already informationalist. But so we will agree on many things in that case. But since I found in my experience a lot of people that are strongly against informationalism, and they are very materialist, I can make an example. Fröhlich is one of those, and maybe you know him. He's pretty famous. I start with the motivation, which is actually a starting point for a discussion. So the starting point is that we need to leave the notion of object to do theoretical physics. And the notion of object is untenable. Can you see everything clearly?
Yes.
Perfect. Yeah. Okay. Is untenable in the sense I'm talking about object as a localizable bunch of properties with a mereological connotation, means that you can make objects by putting objects together and you have a composed object. So the composition rules should be crucial in the definition of object. And one of the main reasons why the object is untenable is the holism of quantum theory. I have also a bunch of transparencies about this, which is the following. So in quantum theory, you have that the properties, there exist properties of the whole, of two things together, of the whole, that are incompatible with every possible property of the parts, of the component parts. Actually, almost everywhere is almost all. So we will see in a short calculation in detail what I mean. I mean that by property, okay, I will tell you later. So let's see first the list of problems. And second, there is a very famous theorem by Malamud that says that it makes no sense in any case to consider a particle as an object, as a localizable entity. And this is a very famous result in quantum field theory. Then we have a particle distinguishability, which is against the notion of object. Clearly, the self-identity principle does not hold, because the particle is not an object. And the transmutation, the fact that you go from one kind of particle to a different kind of particle, the particle disappears and reappears in a different fashion. And the complementarity, the fact that there are properties, the notion of object is based on the notion of bunch of properties that are incompatible, and a la Heisenberg sense, in the Heisenberg sense. The so-called non-local realism is also, I'm saying, the violation of Bell inequalities. It's also in this direction, because the property of an object depends on remote setting. So it's not the property of the object, because it depends on the remote setting. And then I should say, and maybe somebody will not agree with me, that the bomb theory achieved the description of the Schrödinger equation, but only in the non-relativistic setting. Actually, we had very long discussion with Tumulka once, with Charles Bruckner and Bob Cook. I don't remember where we were, in Poland maybe, and he couldn't prove that really there is a way out for quantum field theory. So the problem is that we are not happy just of having quantum theory, but we need to go to quantum field theory. Otherwise, We don't get the mechanical part of the theory. And so the point is that the particle is just a state of the field. So what is the ontology is not the particle, is the field. The state, by the way, is a probability rule. So it's just a probability rule. Probability, according to Bayesian, I am a very strong Bayesian. I think this is the only way to look at probability. Probabilities are subjective. So the particle is kind of subjective entity. Is a probability rule. In fact, it is a subjective entity in the sense that is a rule. So it's a piece of theory. Theory is subjective. And is a piece of theory by which I can determine, I can predict phenomena that are not the particle. I don't see the particle, never. I see only the effects of the particles. Particles are theoretical notions. And Maynard Coleman actually, and I have a very nice transparencies about that, show that, wrote a very long Scientific American, which I strongly suggest you, saying that there is no way you can think to a particle in the usual sense. The particle is not a particle, it's something strange. And yes, I already told that the particle is a state of the field. The only meaning of particle which makes sense in quantum theory is the notion of particle as irreducible representation of the Poincare group. That's the only one, which agrees with the classical vision. And now, so what is the field? Because the particles are states of the field. The field is just an information support. What does it mean? I'm saying it has states, like the bit has states, the qubits has states. Is an information support is made of what? The field is what? Always people ask, what is the field? And you know, we don't like to leave realism in quantum theory, but unfortunately we left realism many years ago when we introduced the notion of just classical field, like the magnetic fields. What is it? Come on, it's not something realistic. Ask to a normal person what is the magnetic field. So the field is information support. So what is an information support? It's a set of bits of, you know, but everything is quantum, is a set of qubits. So I think we can safely say that maybe we are fixed with the notion of continuum, and we say is a continuum of qubits. It is not so relevant. The continuum is another problem. It's another problem which is part of bias in our theory, I think. And so it's a collection of systems. It's a collection of qubits, or anyway, kind of a more dimensional system. So we have now to focus the attention of a new kind of ontology, which has no property, nothing, and which is not the usual one, which is the notion of system. So the notion of system will substitute the notion of object. And I should say that if we really want to do a very fundamental theory, we need as a starting point with the bottom-up construction, we need something which is featureless, which has no feature. Because if it has features, then it's not fundamental, because you need to explain the features also. So the very fundamental notion is that of something which has no feature. And this introduced a new framework which actually can be generalized and can be made very precisely mathematical, which is the operational probabilistic theory framework, which I strongly suggest to call in this way, because many people call the OPTs like GPT, but the general probabilistic theory has no meaning apart from being just not a strict one, but just a general one, which is not interesting. Operational is a very precise meaning that I will show you today. And so this actually is a very strong Copenhagen point of view, as you will see, that leave us without a realistic vision. But the point is that we need to follow the scientific method. This is something that most of the scientists forget all the time. And you will see in which sense they do. And so it's crucial to have a precise distinction between what is objective, what are the objective data, and what is the theory, which is our construction. And this distinction is crucial for falsifiability, because if they are not distinct, you cannot falsify. You need an objective data, which is not theory, to make a proper demarcation and to say this is a theory, is not just a magic. And so once you have this OPT, then you build up a theory, this framework, the OPT framework, you build up a theory, and the axiomatization framework should, I suggest, have inside itself notions that are, that has as a goal the possibility of falsifying propositions of the theory. And actually, most of the postulates that we introduce, actually all of them, this is my personal opinion, that we introducing to derive quantum theory many years ago, that are 6 principles, are essentially principles that allow falsifiability in the presence of probabilism, locally, and causality is another hypothesis that allows you to have falsifiability, and then I will tell you this. We can discuss more if you want to go to more technical things. Then we can go there, but we can also discuss some of these aspects, which I think are, before starting in going into details of a completely new point of view, which is a kind of new field in physics, was strongly motivated by Feynman himself and by his teacher Wheeler, that physics is information, and there was a good reason for that. Before going to detail, we need to understand if it is worth doing that and why. And so quantum theory, when I say quantum theory, I should remark that I don't mean quantum mechanics. So there is just the theory without any mechanical connotation. So the rules of self-adjoint operators, unitary transformations, states that are positive operators, this kind of rules. Then if I want to get out from these rules quantum field theory, I need to add other rules. And just what I do the following. I take a denumberable set of infinitely many systems. So the field is a denumberable set of systems. Numberable allows you to connect them. The continuum becomes a huge problem. But this is the fact that the word is actually continuum is just metaphysical. And then from the numberable set of infinitely many systems, I build up an algorithm, which is the easiest algorithm I can, in the sense of algorithmic complexity. You will see what I mean. And then what I find is that the easiest algorithm is quantum field theory. I'm saying this way we derive not just the whole quantum field theory, we derive free quantum field theory. For the interacting one, the work is still in progress, is becoming a little bit complicated, as it has been also in the history of physics up to now. And so, just very short presentation of which kind of postulates we use to derive quantum theory. So quantum theory is quantum mechanics without the mechanical connotation, just the set of rules of the grammar of physics, namely observables, unitary transformations, actually not unitary as we will see, generally probabilistic transformations, and states as a positive operators. And they are derived from 6 postulates that are causality, this blue one. Can you see my pointer on the screen?
Yes, yes.
Oh, great. Causality, local discriminability, purification, atomicity of composition, perfect discriminability, ideal compressibility, that I will tell you later. And so we get quantum theory from these postulates that are precisely formulated in the OPT framework. And then I take the numberable set of quantum systems, and I add additional principles that are all of the kind of minimization of algorithmic complexity, that are locality, homogeneity, isotropy, and unitarity. And then I add other simplification like linearity. And then I will tell you more in the following about what I take the easiest situation, which is that of an abelian group. I have to tell you why the abelian group comes in. It comes in because from these 4 postulates that are, by the way, there is also discussion about these postulates in terms of conventionality of quantum theory. Conventionality of in physical theories, and so these are actually postulates you can live without. And then these postulates imply that there is a structure which is a quantum cellular automaton on a Cayley graph of a group. So there is a group coming out, which is a kind of symmetry group in a sense. And then I'm just telling things very sloppy now at the beginning. Then we go into serious detail if you want. And so the group, you take the easiest group. So you take the easiest situation, which is a linear evolution. So instead of being just a quantum cellular automaton, it becomes a quantum walk. And then you take the easiest group, which is the abelian one. And what you get Weil, Maxwell, and Dirac, so free quantum field theory, and you derive the special principle, you derive special relativity without assuming special relativity before. So it is the reverse way of Dirac, that he derived his equation imposing relativistic covariance. Here, relativistic covariance comes out as a result of these postulates, which, as you see, has nothing to do with space. There is no assumption about space and time. There is no space notion, just a set of systems and unitary evolution, linear. So the easiest evolution you can think. Okay. Okay, great. This meeting has been upgraded by the host and now includes unlimited minutes. Great.
Yeah, same here, so we don't have to worry.
Great. Okay, so there are many other things here that it comes out that, for example, the mass is bounded. And so there are things that have a flavor of a GR, but unfortunately, we have no idea how to get GR out of it. Otherwise, you know, I will be somewhere very famous. Okay, and let's see. Now, I think we can proceed to question time. So if you, it's how much time did I get? 23 minutes. Okay, so pretty 15 minutes, a little bit more. Here I have a set of topics where I can press and get the transparencies, so we can discuss. Let me come back now because there is a set of transparencies for each one, and some sets are made of just 1 or 2 transparencies. Some sets are longer, like for example, the PT framework. If there are people interested in, for example, the mathematician, I think he knows almost everything already. Sorry, what can you remind me your name, mathematician?
Alessandro.
Alessandro. Okay, Italian. So, and then we have technical questions here. Maybe I just review these questions, but you are free of making your own question. Actually, I am more interested in questions that are not here.
I have a curiosity. It's about the Malaman theory that you mentioned before. So I would like to understand, I mean, it's a theorem in which context? Because for me, the fact that the particle has a you know, massive point does not make sense. It's just a consequence of the fact that, I mean, I consider quantum mechanics as a theory in an Hilbert space, so some L2 space, and already for me already the mathematical formalism contains this information. So
the mathematical formalism that contains the information that the particle is what?
Is cannot be localized,
right. Yes.
Point, right? It's
yeah.
state.
No, the point is that if you ask to a normal theoretical physicist, he does not know even who is Malamud.
Oh, okay.
So
no, I mean, I don't know myself.
if you ask to a philosopher of physics of quantum field theory, he knows everything very precisely. I am not neither of the two, but I know this theorem. So the localization issue in quantum field theory. This is a pretty famous theorem of Malamud. This is he found this in a very famous paper by Halvorson, Clifton. Okay. That you may know. If you are an expert of quantum field theory, you know this paper is very famous.
But I really am not really an expert of quantum field theory, more in non-commutative geometry. But okay, let me see.
So the theorem says this one is very simple. It's much easier than non-commutative geometry. So you have an Hilbert space. You have a POVM. Actually, the POVM version has been made later by Bush. This is a spectral measure. It's a PVM, positive value, projector valued measure.
Sure.
This is a set in space delta, and then you have a positive operator dependence, and then you have a unitary depending on A, which is a vector in the space where you take this delta, which is the usual space. So this is a localization system over Minkowski space-time. Satisfy localizability. I report here the notion of localizability means that if you take delta and delta prime disjoint, the product of the two projections is 0. Then you take translation covariance, that if you translate delta, this corresponds to unitary translation of the PVM, the projector valued measure. And the energy must be bounded from below. This is actually the crucial point which makes everything bad. And the people always forget. And why we need the energy bounded from below. I'm sorry, otherwise we get the eternal motion. No, that's not true. And micro-causality is the usual one, the commutation if you have disjointed sets. And then the POVM is identically 0. So it's a contradiction.
Sure. Okay.
And then there is a stronger version, I think, which is this one and other. Let's see if I can. So which page is this? There are even stronger versions. For example, for POVM made by Bush. Paul Bush died no more than 1 year ago, I think, or 2 years ago. And so, they are the same as more general and more reasonable and even worse. So the notion of particle as something that you can put in a place and is localizable makes no sense. And there is a problem with, for example, is well known, the position operator in quantum field theory is a mess. So there is nothing which is a reasonable position operator for the photon, but also for massive particles. So, and you see here is the conclusion. We then went on to show that relativistic quantum field theory does not permit an ontology of localizable particles. And so, strictly speaking, our talk about localizable particles is a fiction. Nonetheless, relativistic quantum field theory does permit talk about particles, albeit if we understand this talk as really being about the properties of and the interaction among quantized fields. So the ontology is the field. Actually, let me see if I find also the Maynard-Kuhlman. So Maynard-Kuhlman, I strongly suggest you to read this beautiful article on an issue of Scientific American about the localization issue. Is very, very nice. The particle interpretation stretches our conventional notions of particle and fields to such an extent that ever more people think that word might be made of something else entirely. And the whole paper says a lot of things which are even worse than that. and with very strong logical motivation. So the localization issue is the one that is really strongly against the notion of object. So coming back to the theoretical motivation, I think that there are too many reasons to abandon the notion of object, but the holism reason is one of the strongest one.
Okay.
Let's see why I get this. Sorry.
Vincent, do you have a finger there?
Yeah, I would have a question. So what do you think about the Bohmian attempts to define a QFT? They claim that whatever a free QFT can do, they can do the same.
Yeah, they actually, you know, the point is that you have to become a Bohmian to understand Bohmians, because you have to study a lot of stuff. So the best that I did with other two guys that I have a good esteem of, Czaslaw Bruckner in Vienna, you know him probably, and
Yes.
and there was also Bob Cook, who is not really a guy in this field, but I'm saying Bob Cook is working in information science. He's a computer scientist. I'm saying he's a physicist who became quite a computer scientist. Category theory, and we had a very long dinner together with Tumulka. Tumulka is supposed to be the expert, and every time I ask to a Bohmian about quantum field theory, they say ask to Tumulka, and and actually we had a very long discussion about 2 or 3 hours, but it was not convincing. Unfortunately, you know, whenever you go to a Bohmian paper, either is unreadable, like this Tumulka one, or is the usual stuff. And there is a lot of statistics, mathematics, and things like that. But, you know, unfortunately, the notion of something objective which disappears and reappears is pretty strange, right? So, but it's not that. The problem is that the covariance is the problem, the relativistic covariance. I've never seen really derived in a realistic way the Weyl equation or the Dirac one. For example, our derivation of the Weyl equation, the Dirac equation, or Maxwell. Oh, for example, Maxwell. Oh, come on. Is there a theory of electromagnetic field in the Bohmian theory, in the Bohmian framework? I really don't know. You need to ask a Bohmian for this thing, because personally, I don't believe that. And I had very long discussion about Bohmians with Alberto Rimi, who died years ago. And he says that, unfortunately, in all these theories, and including is one which has nothing to do with Bohmian, but, you know, there is a feeling between Bohmian and GRW, Girardi Weber Rimini. And they say the problem is that whenever we go to the relativistic case, we are in trouble. Whenever we go to indistinguishable particles, we are in trouble. Whenever we go to photons, we are in trouble. So this is the only thing I can report. I'm not an expert of Bohmian theory. You need to ask to a Bohmian, and then the Bohmian need to convince you. So I convince you to the opposite point of view. And then if you want to convince of the other one, ask to a Bohmian, not to me. Because
Fair enough.
Anyway, I have at home, I have like 10 books about Bohm theory because I've been very fascinated by that. But, you know, after a while, it becomes bored. And because the motivation is not a logical one. It's not a logical motivation. What is the motivation? The one of the realism. This is not a good motivation. We can discuss about that, because why a theory should be realistic? For which reason? Just to say, the reason is usually related to the so-called notion of understanding. Understanding, what does it mean, understanding? The theory is something that makes me understand. If you think about what does it mean understanding, is completely meaningless, because you understand in terms of something else that you already understood, you think already understood. There is a very nice movie with Feynman interview on the web. It's very famous, where a journalist asked him, when I push two magnets one against the other, I feel something in between. What is it there? And then Feynman raised his eyes to the sky and said, you know, I need to explain you what does it mean to explain. And, you know, explaining what is the magnetic field, please, is realistic. So, and the OPT framework, if you see the framework, if you know it, I don't know which way you know it, but if you see it, you understand what does it mean to get out of this tunnel, the tunnel of realism. But, you know, most of the people, especially philosophers, are realists. And they want to understand. The point is that there are different kinds of understanding. Understanding in terms of a model that I already have, understanding in terms of logical argument is a completely different thing. Sorry.
Can I ask some question?
Yes.
Yeah, go. I think we'll come back to realism at some point.
Yeah. So I have a lot of questions, and so I just have one question on realism also. So the first question I wanted to.
My computer was speaking. Can you start again?
Okay, I'm going to start again. I was just saying that I have a lot of questions, so I won't ask anything at the same time. But my first question is: so there are different axiomatization of quantum theory that are based on information, and I wanted to ask you. So, what was? How do you compare to the other ones? I don't know. For instance, RD1 or I know that a little bit different, but Rovelli also has some axioms based on information.
Yeah. No, but
how they relate to yours, and what are the difference? And of course, I would also like you to talk about the purification postulates. That seems really important.
For me,
a quick finger there. So can you also add, because I had a similar question, can you also tell me if there is some principle that you believe you share that virtually everyone who does the same job share, just out of curiosity? It seems that something like the locality principle should be in the background for any reconstruction. So I was just curious if you believe there's something that everyone should have. Or
actually, yes, thank you. This is probably the most important thing to discuss. Why some set of principles? Why other sets of principles? So to me, there are principles that are merely mathematical, and I can present quantum theory with 3 lines, and there is no need of coming back to the old von Neumann axiomatization approach, which actually is abundant. There are things that are not relevant, that are logically coherent with the theory, but they are not essential in the axiomatization. And the problem is that you need to distinguish the mechanical part from the theoretical framework, because they are 2 completely different issues. And the right way is to derive from the framework and from the principles of quantum theory, quantum field theory. That's the only way to get it. And then get back the Schrödinger equation as a special case, as a special instance of quantum field theory in the non-relativistic case. To me, there are principles that are better than other because they have, for example, an epistemological connotation. Namely, if you don't have this principle, you cannot do science. And this is the kind of principles that we have. And the other people, most of the people, they say, oh, that's too much. I don't believe you, or, you know, but so you have to judge yourself. You have to judge yourself. And so I don't think there is somebody that is claiming the same. So the point is that it needs time to check out the derivation. The only thing which is negative is the derivation that we have is too long, and we need to find time and energy to make it short, and then people will believe us. And that's I'm sorry, the problem is that you may have the perfect logical construction of everything, and then you are in trouble because you build up the theory and it becomes complicated. This is something which has nothing to do with the logic, the fact that the things becomes complicated. You cannot predict from the logic that the things are going to be complicated. Unfortunately, this is part of our human limitation and the history of our knowledge. But the point is that if the motivation of a theory are epistemological and they are part of the scientific method itself, you may discover that most of the things that we know are the only possible things that we should know, because they are the way in which we know things, not just the way in which the work is done. So I don't know, if you want to see this kind of stuff, I have some transparencies, but you need to first, I don't know, I can discuss first the motivation of the principles without telling the details of the principles, if you already have an idea of which are the principles of quantum theory that we use. But if you want to see the principle, you have to say.
You can show us the principle. I mean, I know them, but I'm not sure that everyone in the conversation has the knowledge about your principles. So.
Everybody is familiar with the OPT framework and with the principles?
Not really.
Not
with
really.
relation to the OPT framework and stuff, I'm familiar with that, but its relationship with quantum field theory is something I'd like to see at some point. I don't know if that's a bit technical.
Yeah, quantum field theory is derived from quantum theory with additional principles. And you don't need the framework, you don't need the principles of quantum theory to derive quantum field theory. Quantum field theory is something in addition. So there are additional, you already have the quantum systems with the rules, and you take infinitely many of them and you add the principles. So if you want to see this is a separate thing. So we have three things to understand: the OPT framework and why it is the only framework which has methodologically meaning and is falsification ready and things like that. So it's not any framework. I cannot invent a theory because it's pink, because I like it, because it's blue eyes. I'm saying I need motivation for a framework. And then within the framework, I formulate postulates. I cannot formulate postulates if I don't have a grammar for the postulates. So this is one thing. Second thing is derivation of quantum field theory. This is easier to understand in terms of conceptual issues. And so, and if you want to see the principles, we can discuss them sloppy, or we can see the precise definition, which is not really so mathematical, but it needs some a little bit of time. So let me know what you want to do. OPT framework?
I'd prefer the more mathematical definition if that's possible, but other people may feel differently, and I'm happy to be outvoted on that. So
you want the OPT framework, you want to see the OPT framework and the principles of quantum theory and then discuss the epistemological meaning of these principles?
Yes.
For me, yes, but maybe others don't.
Okay.
I would try and do that and then probably come back to the epistemological side, because many people, it's interesting. And there are also a couple of other questions, and we have 1 hour and 15 minutes. So let's start from there.
Okay. So the OPT framework. So, no, wait a minute. First, I need to do something different. I need to explain what is an OPT. So what is an OPT? An OPT is the following. This is something that few people understood. The reason is just, you know, the way in which papers are presented. So we have events, D, H, C, this in, and we connect events by input-output relations, which are the systems. So these are theoretical entities, the systems. So and now I have a probability, which is the joint probability of events. By the way, each event is a set of a complete set of possible events, which is called test. And the probability, the joint probability of events generally depend on this graph of connection, in the sense that if I take marginals, usually the marginal, no, let me come back. The if I want to know the marginal probability of event K and J, I sum over H, G, C, D, and everything else, but they still depend, the marginal probability, it does not depend on the variable H, G, but depends on the connection from the test with the test here. So the marginal probability of events depend also on the marginalized part. So there is something more than a joint probability. It's not just a probabilistic theory. There is a dependence on a graph of connection of the marginals. Even though I marginalize, the graph is still there. And for example, something that you can understand easily is a rule which is part of the OPT framework, which is that if I have two disconnected graph, so I'm considering here just a graph of connection, which is a unidirected, D-directed acyclic graph, DAG. And this is an instance in which I have two disconnected parts of the graph. So if you have two disconnected parts of the graph, then the joint probability of one part is disconnected from the other, in the sense that you have a factorization of probabilities, right? Statistical independence in the presence of no connection between portions of the graph. This is one of the rules of the framework. So this is crucial. So because if you think about, there is nothing that you can do better than connecting events, objective events with the theory. So you make a connection of everything is connected by a theoretical thing. Everything you see is connected by a theoretical thing. So there is a notion which is very objective, and the notion which is not, which is a theoretical one. The objective notion is that of events everybody can see, and then there is the system which nobody can see. Is a theoretical notion, is not objective, is theoretical. So for example, if you have two Stern-Langerlach apparatus, one in front of the other, the left and the right one, if you change the setting of the left one, you change the statistics of the right one, but vice versa you don't. So it means that if there is a connection between the left and the right, and you say there is a particle flying between them, but you don't see the particle. You see just the clicking of the lights. And the particle goes from left to right, because this is actually the formulation of the causality principle that I tell you later. But there is a connection because the probability of what's happening on the right depends on what you do on the left. Even though you marginalize, when I say the probability of what's happening on the right, I mean the marginal probability, because this is the notion of probability of something on the right, is marginalization with respect to the left. But this probability depends on what is on the left, even though I marginalize on the left. And so here, for example, the left is independent on the right. The right depends on the left. and we say there is a particle, but you cannot see the particle. You see only the click of the detector. This is what the poor Bohr guy was always saying all the time. And the OPT is actually the goal of science, because you connect objective things happening, and you devise a theory of these connections, and you make prediction for the future occurrence of, in the same, when you suppose there are the same connections, predict probabilities of events depending on the connections. So which events happen is the objective datum, and systems are theoretical. So the fact that you can distinguish between the two is crucial for falsifiability. Otherwise, you cannot falsify if you don't distinguish what is objective to falsify what is theoretical. Most of the time, the identification between theory and objective data, like in classical theory, you falsify a law, something inside the theory, but not the theory itself, not the grammar of the theory, because the grammar is automatically descriptive. So the point is that quantum theory is a grammar for physics, it's not the physical law. So it's the rule. And so anyway, I insist, you have to provide a mathematical description of systems and events. So when you make joint events, you have to make composition rules for the systems that corresponding to joining events and things like that. And if you think about, this is just a directed acyclic graph, which is bounded because you connect events by systems, is bounded because you consider a finite set of events, and then it must start with events that have no input systems and events that have no output systems, finish with events that have no output system. And if you think about, this is a directed cyclic graph as it is a quantum circuit. So that's the connection with quantum information, that connecting a set of events by unidirected graph is a quantum is the same kind of circuit that you use in quantum information. And these are state preparations on the left, and these are observations on the right. And which is, I'm saying, this is something trivial, is the run of a program on a computer. Is not the flow diagram, it's the run. There are no loops. So this is actually the end of the story from the point of view of just having the conceptual starting point for what is an OPT. Now, if we want to go to the rules of the OPT, the framework, then we need to make things precise. So you have joint probabilities plus the connectivity, and the connectivity, sorry, I did some mistake. The connectivity rules that make the marginal probability depending on the circuit. So the notion of events is not just a probabilistic notion, but there are input and output wires that are what we call systems. And I already explained what is a test. We can go pretty fast here. I have this closed circuit, which is something by which the joint probability depends parametrically. The joint probability depends parametrically on the circuit, and the connectivity rules can be synthesized very simply for those who know category theory in terms of a strict monoidal symmetric braided category, if you want to get quantum theory. And generally an OPT is a strict monoidal braided category, maybe not symmetric.
What does it mean, strict? Because
yeah, strict, I can tell you in a while, because we need to see the monoidal, the monoid, where it comes from. So the point is that we need to make rules to connect events, and so there are special kind of events that have no input, like the preparation events, and we introduce in this way the notion of a trivial system. So actually, I'm not giving the formal definition. I'm giving something in between formal and something that I can tell you in a short time. And then there are effects, the so-called observations, sorry, that have output system, which is a trivial system. So you define sequential composition of tests and then of events in this way. You have composition of the test from A to B, and the test B to C becomes a new test which goes from A to C. The probability space of the outcome, becomes the Cartesian product of the probability spaces, and rules of this kind. And you see here that the systems play the roles of the object in category theory, where the events or the test play the role of morphisms, of maps. And then we introduce the identity test, which is a deterministic test, and whichever deterministic test C you have, it is equivalent to write this way. So you represent it just by making the wire long if you want. You can stretch the wire, and the stretching of the wire corresponds to make identity test or identity events. Is a singleton test when it is deterministic, the event. And then you have parallel composition. And in the parallel composition, you introduce the notion of composition of systems, which are A and C into the system AC, and B and D in the system BD, input-output systems. And you have to introduce the notion of swap, which is represented here by this wire, by this graph nodes wire. And the swap from AB and BA. And AB is isomorphic to by BA, but not necessarily equal. If it's equal, then you call the category symmetric. And
sorry, what do you mean by equal here?
Equal, for example, you say in quantum case the mathematical description of system is an association with an Hilbert space. So you have an Hilbert space describing the system, which is H of A. Now the composition of the two systems in quantum theory become the tensor product of the Hilbert spaces. So AB has an Hilbert space, which is the tensor product between H of A and with H of B. Now you can identify the tensor product with the same. So you can say that you say that the tensor product between HA and HB is equal to the tensor product between HB or HA, or you say is not equal, is isomorphic, right? And this is the difference.
So it's not just assuming that they have the same dimensions.
So yes, exactly. If you assume that they have the same dimension and that's all, then there is an isomorphism here instead of an equal.
Okay.
So otherwise, you can say no. There is an isometry connecting the two, which is a change of basis, for example.
Okay.
And then you need some additional requirements that you can see that they cannot be derived, but you have to assume that are, for example, these naturalist assumptions that if you move the events G and F over the wires with a swap, you get the reverse of the two in parallel. And so this is what we call braided for the category theory.
Oh, okay. Okay, sure.
And then
so it's naturalness in the sense of category, really. It's natural in the sense of functoriality in this case, right?
yeah, I think so. I'm not an expert of category theory, and even less than the philosophy of category theory. Okay. So, and then you have the notion of the trivial system, which is identity A is equal to A. By the way, I forgot to put it here. And A, B, C. The association of system is associative. As associative, association is associative. And when is exactly associative, instead of being isomorphic, is called strict monoidal. Monoidal because there is identity element also, right? This is the name coming, I think, historically. And it is strict monoidal when there is the equal here. It is just called monoidal if there is just an isomorphism. In exactly in the sense that I said before. And the category is symmetric if the swap is in an involution.
So maybe, again, I am not very comfortable with the notion of something being equal and not just isomorphic in a category, because I mean, when studying category theory, we are used to consider things up to isomorphism. Mm. So just from understanding, when you say that the few things are equal, not just isomorphic, perhaps do you mean that there is some unique canonical isomorphism?
Right, right.
Okay,
yes.
so I don't have to make any choice. That's
I think there's also a MacLean's strictification theorem, which is key to all of this diagrammatic stuff. That for each, I've forgotten all the details, but basically, if you want a strict diagram that gives you absolute equality, you can get that. But yeah, if you look at the strictification theorem, you should be able to find something that will satisfy you, I think.
Oh, I see. Thank you.
Yeah. Anyway, I'm not an expert of category theory, but what I can tell you is that the case of quantum theory is very simple. So this is the tensor product, the identity system as Hilbert space of the corresponding Hilbert spaces, and the identity system is as a Hilbert space which is C. So if you take the tensor product of an Hilbert space with C complex numbers, which is an Hilbert space of dimension 1, you get the same Hilbert space. What I want to tell is that these rules looks just you know, a game, but if you want to build another theory which is not quantum, then you really need to check these rules, and so you need to go to the pentagon rule for the associativity, or the hexagon rule if you have the swap and the associativity, triangle rule. You have to check all these things, and this is not trivial when you build up a new theory. Like, for example, real quantum theory over the reals, or you know, PR boxes, or classical systems, non-local connection between them, or things like that. When you build up a new theory, then you have to check all these rules, and this is not trivial. This is the difficult part that people don't know, that you have to check this. And then you have another naturalist condition. So this is another assumption that you have to make, that the parallel composition commutes with the sequential one. And this actually is the one which guarantees the meaning of the stretching of the wires, because there is the composition with the identity. And then I can tell you things that have nothing to do with category theory, like that you can make a coarser description, putting a circuit inside a box, or you can make very, very coarse description or finer description. For example, going to a situation which has a graph, which is that of a quantum walk, which corresponds to go to quantum field theory. Quantum field theory, you need infinitely many systems. Here, the events are the rectangle and the systems are the wires. The systems are always wires. And you see that there are infinitely many. And the rule is given just by which are these two inequivalent transformations. I need to tell you what is a transformation. Sorry. So we have this notion of events and tests. Then you make equivalence class over all possible probabilistic equivalence class of we need to associate. Sorry, I think I forgot to put it. Yes, I forgot to put the probabilistic part. Anyway, we need to associate the probability to every single event and the events of all tests. So there is this part which is actually this is something that has never been published, and there is Paolo Perinotti with Marco Erba that are doing this. There is probably a way to derive the probabilistic framework as a functor, but this is something that is not in my work, so I cannot tell more about that. And so the probability associated to the different tests and different events, you make equivalence classes over all possible tests or events occurring with the same probability within the same closed circuit. And you call these transformations. And there are transformations that have no input, and these are called states, or trivial input, and transformations that have trivial output, and these are called effects. So that's the end of the story about the framework. And then there are principles that you build up within this framework, defining this framework, and derive the theory. And if you change the theory, you change the principles. But let me say now, the presentation of quantum theory mathematically, which is just made of 3 axioms, is not like the historical von Neumann axiomatization that has so much stuff, because there is the Schrödinger equation, which is mechanical. So the notion of system, the system is associated with an Hilbert space, the system composition is associated with a tensor product, and the transformation from the system A to system B is, with input system A and output system B, is a completely positive trace non-increasing, this symbol means trace non-increasing, map from trace class operators over Hilbert space HA to trace class operator over Hilbert space HB. So there is nothing more than that. Everything else is theorem, because transformation from trivial system, which is the complex Hilbert space made of the complex, to a non-trivial one is a state. And the trace class completely positive maps becomes just positive operators with trace smaller or equal to 1, bounded by 1. And the observation actually are the so-called effects, the equivalence class of all possible observation occurring with the same probability within all possible closed circuit, are called effects. And these are trace, partial trace with a positive operator which is bounded by the identity. So there is no need of introducing unitary transformations. Unitary transformations are just a special case of transformation that are deterministic, and you can write there is a dilation theorem that says that you can write every possible probabilistic transformation as a composition of a von Neumann measurements local over a unitary interaction, but there is no need of it. So you don't need to have the unitary all the time. This is not required for the coherence and completeness of the theory. So the fact that it can be dilated does not mean that it exists. So actually, there is a discussion that we can do about that, about the fact that all the interpretation of the theory are actually interpretation of something which is not needed in the mathematical axiomatization of the theory. So the unitary. Anyway, this is another point of discussion. There are many things to discuss. Anyway, if you want to see the principles, I don't know what there are so many things to say. Maybe we can do another talk. What time is it?
Can you hear me? So Ippo, you don't have the microphone on. So let me just wrap up 1 sec. So we have a lot of questions. So Ippolita guess only apparently short one, and also other questions. And then there is Richard who had a question, and then Patrice who wrote his question down. And then Maria has a couple of questions, and I'm sorry if I missed someone, let me know. So we have 50 minutes. So yeah, I don't know how to do that. Let's try. Let's see.
So maybe just to finish on the OPTs, just show us really quickly, really briefly the postulates because that was the point of my first question. But don't go into the details, please, because we won't have the time.
So we don't enter details of the postulates. We just give the definition of the postulates.
Just, yeah, maybe give the flavor of what means, what is quantum.
Okay, so I go fast. I go fast here, right?
Yeah, because there was a lot of different questions.
Yeah, unfortunately, there is a lot of stuff. I'm saying it's a completely new way of doing physics. So these are the postulates: causality, local discriminability, purification, atomicity of composition, perfect distinguishability, and lossless compressibility. And the causality is the fact that, so there are preparation and there are observation. And if you cut every closed circuit can be divided into two parts. One is a preparation, because there are input system which is trivial and the output systems are not. And the other one is an observation. And the probability, the marginal probability of the preparation is independent on what is the observation. This is the causality. Okay, we can discuss about that later. And these are huge consequences on the theory, because it gives the convex cone structure for the theory. The deterministic effect is unique, is an if and only if condition, and so on. Local discriminability. So you have joint states that are different of two systems. Then there are always local observation by which you can distinguish joint states. This is a crucial point, because years ago, in a conference, there was a pretty famous guy, Vladimir Bucek, who is a nice friend, who said, come on, you are doing tomography of an entangled state by local measurement, but it's entangled, how can you do that? No, you can do that, because there is this principle that reconciles allism with reductionism, because you have allism in the sense that the knowledge of the whole does not imply the knowledge of the parts. No, if you have a maximally entangled state, it's pure, right? So you have the knowledge, maximal knowledge of the whole. But if you take the marginal states, as you know from quantum physics, these are completely mixed. So the knowledge of the whole does not imply the knowledge of the part. So you have allism, but still you can observe an holistic situation by local observations. And this is crucial, otherwise you cannot do science. And for example, the fact that you have this principle allows you to to say that you can always classify a transformation from its input-output condition. Otherwise, you cannot do that, because you need to go to a closed circuit here, because you cannot have an observation of this kind, and the map always, even though we draw it on a single system, you know there is the notion of completely positive maps now in quantum theory. You need to know what it does in the presence of another general system. So actually the characterization of the map needs some observation here with a joint observation. The fact that you don't need a joint observation then implies that you could just make this in this way as a preparation, this blue one, and you just have the input-output connection that we usually do all the time for maps. Otherwise, it makes no sense. So I'm saying I can answer questions if you have, and then you can make tomography of any kind of system by just local measurements. You can reconstruct the state by just local measurements. This is crucial. It's local observability, which is an epistemological rule. Causality is also an epistemological rule because it guarantees protection from the future. If there is something that from the future can scramble your experiment, right? Because there is an observation later, you have no guarantee of falsifiability of your experiment, because it becomes what you see depends on what is done later, not by you. And actually, the isolation of the experiments needs causality all the time. So these are epistemological both, and then
maybe a quick question.
Yeah.
A quick question on local discriminability. Am I correct that real quantum theory doesn't satisfy this
Real
postulate?
quantum theory does not satisfy this postulate. It satisfies a weaker one, so bilocal discriminability. So you just need to use bilocal observations, which is something which makes weaker reductionism, but it's still reductionism because you don't need three local or four local.
Okay, thanks.
And then we have atomicity of composition. So if you compose two transformations that are atomic, namely they are not decomposable into other transformations, you still have an indecomposable one. And so you are not introducing lack of information. If you have total information on one transformation and total on the other, when you compose them, you don't lose the fact that you have total information. So the composition does not introduce lack of knowledge. So again, is an epistemological one. Perfect distinguishability means that if you have one state on the border of the convex set of states, I have not introduced this notion to you, but most of you know that set of states make a convex set. Just as a general notion, you don't need to go to quantum theory. And so if you take a state which is on the boundary of the convex set, then there is always another state which is perfectly discriminable by it, in the sense that you have probability 0 or 1. 0 if it's on this state and 1 of this is on the other state. So you can perfectly discriminate that. So perfect discriminability is probability 0 or 1, means that you have a probabilistic theory, but still there is the possibility, by definition, because there is always a boundary for the convex set of states, there is still the possibility of formulating a proposition which corresponds to a deterministic event. Namely, if you want to falsify, you can logically falsify because the probability is 0 or 1. So I say this must happen, and then it does not, is a logical falsifiability. Otherwise, in the probabilistic context, if you don't have logical falsifiability, you are in trouble. Everything is up to some p. And then you have lossless compressibility. So let's say this is not the typical convex set in quantum case. It's very complicated. It's not so simple like this tetrahedron. But if you have a convex set, the boundary of the convex set is made of convex sets. And the boundary is made of faces. The faces are convex sets. And each face is made of other face, which is another convex set segment, and so on. Each of these convex sets on the boundary is the convex sets of another system which is smaller, like, for example, is the smaller dimension as an Hilbert space. And so you can compress by a transformation which is reversible. So you can make ideal compression because you really reduce the Hilbert space. Just to say about the case of quantum theory, you can really compress and you can do reversibly. So in a lossless way. So also this one, I'm saying you want to communicate, you don't need to waste communication, because if you want to formulate a proposition, you can do it with the minimal set of theoretical assumptions. And then finally, we have the purification. The purification is something, so formulated in this way, you need causality because you need the uniqueness of the deterministic effect. But it can be formulated also without causality. And it says that for every state, let me say just state. We know now what is a state. It's the equivalence class of preparation. For every state, there is always a pure state such that such state is the marginal. So I ignore one system by making it the probability one observation. And this purification, going from one state which is generally not pure to one state which is of two systems and is pure, is not unique, but any two purifications are connected each other by a reversible transformation. If you think about quantum theory, this is the case. Now you say, and what is the epistemological meaning of this? Means that every kind of a lack of knowledge can be regarded as a situation where there is perfect knowledge. Can be regarded. It's not that the purification actually exists. Can be regarded in this way. And so I can certify a probability because I build up the probability with something which is falsifiable. Because this is a pure state, I can tell you this state has probability 0 on some effect and probability 1 on another effect. So I make you, I tell you things that can be falsified because the probability is 0 or 1. So I prepare a randomness in terms of something which can be certified by a falsification. So I think this is also epistemological. And then it has a lot of consequences, a huge number of consequences. For example, the two normalized pure states are connected by reversible transformations, which is the case of quantum theory. There is the steering that you can prepare states by just one given state and observation. And process tomography, there is a one-to-one connection between the, if you act with a transformation over a state, you get something which is a one-to-one connection, is an injective map, is a one-to-one connection of a transformation. So you can make tomography of a transformation by making tomography of the output state, which is something that actually I introduced 30 years ago before understanding this comes from purification. And then there is the teleportation, can be defined without using quantum theory, the reversible dilation of channels. So the dilation of deterministic transformation as unitary transformation and discarding one system, and also for instruments in terms of unitary and von Neumann comes just from purification. But the point is that I say that it can be purified, but the purification does not exist ontologically. This is something more. Where what we say in quantum theory say that this ontologically exists because all transformation are unitary. This is false. I'm saying it's not false, cannot be proven. Cannot be proven because I see effectively probabilistic transformation. Then I say, no, but everything is unitary. Why? Because there is the Schrödinger equation. Come on, the Schrödinger equation is mechanical. It has nothing to do with the rules. So anyway, if we want to discuss about this thing, this is a point which I have in the list of discussion. And let me. Okay,
so
I finished.
Well, I guess there will be new questions, but I'm gonna go in order. So there was a question from, I guess maybe Polite still wants to add fingers or other clarification, but I'm gonna first ask Patrice, and then hopefully I get back to you. All right.
I'll ask it.
Patrice, you had a question. You can go.
Well, I feel like you can skip mine and go for the others.
All right. Well, I actually have Hippolyte again after Patrice, so it's your time.
So just two things. So one thing I wanted you to clarify. So all the postulates you show us, if I remember correctly, only the purification distinguish
yes.
quantum theory from other OPTs, right?
Right.
Yeah.
Actually,
so what makes quantum? The answer to the question why is the quantum, to you it's purification.
Let me go to another okay, this is a
and so yeah, sorry, and also another just a little question that is linked to this is so there is one of your slides where you say that quantum theory is a grammar of physics. What do you mean, like philosophically? Maybe what does it mean to you, like the grammar of physics?
Let me, first of all, about independence of postulates, which theory has one postulate, which theory has another postulate. I have a transparency, let me find it. Other OPTs, okay. So here we are filling a table of different theories on the y-axis. So QT is quantum theory, CT is classical theory. Then there is the quantum theory of qubits, fermionic quantum theory. I don't remember this one. I'll try to remember now. PR boxes and many other theories here. And here we have some postulates. The yellow one are the one for quantum theory: causality, perfect discriminability, atomicity of sequential composition, because there is also atomicity of parallel composition, compression, purification. And as you see, quantum theory satisfies all of them. And no information without disturbance, this is very interesting. And classical theory, you see, does not satisfy purification. Once you have a theory, I want to remark, that satisfies all the postulates apart from one, this works as a model, the theory works as a model of your axiomatization, and then it is a guarantee that these postulates is independent from the other. So we know that purification is independent on the other 5 postulates because we have an instance of a theory that satisfies all the other, but not purification, right? So it cannot be implied by the other. And so this is the case of classical. In classical theory, you cannot purify. If you have randomness, randomness is always can be always interpreted as lack of knowledge. In the quantum case, randomness is not a lack of knowledge. because you have perfect knowledge of the state, which is the maximum knowledge that you can have, but you get probability by creation of randomness. It's not just by lack of knowledge, because you have the most perfect knowledge you can ask. So the probability is not lack of knowledge. This is the reason why in one case you have it, the other case you don't have it, if you want in short terms. And then we have other instances of the same problem of independence of the postulates. There is, if I take a special case of quantum theory, which is the theory only of qubits, namely that the systems are only qubit, composition of qubits, composition of qubits, composition of qubits, and no qubits, for example, or things like that, then it does not satisfy the compression postulate, because if I take two qubits together, the face of the convex are qubits, but they are not elements of the theory. So the compression postulates does not depend on the other 5 postulates, because this satisfies purification clearly. And the real quantum theory does not satisfy local discriminability and satisfy all of them. So local discriminability is another postulate which is independent from the other. For the other postulates, we still don't know. We are trying to fill up this table, and it takes time. This is actually maybe just for a check, you take to write a couple of papers, and it's not a trivial one. But what is interesting is no information without disturbance, which we regard as a postulate. We very recently discovered, and this is our last paper on the web, one of the last paper on the archive, that no information without disturbance, the only theory which does not satisfy it about all possible operational probabilistic theories is the classical one. Or it satisfies some time and some not if there are classical systems in the theory which is non-classical. So no information without disturbance is everywhere. Apart from classical, the only theory which allows you to have full information without making any disturbance is the classical one. This is something very interesting, I think. So these are the things that you can do if you have a very good framework to work, postulates that are formulated in the framework. Everything is serious. It's not just, try and see what's coming out without a precise definition. Everything is. Anyway, other questions?
So I had
just a quick one.
Yeah.
What do you mean by the question marks here?
The question marks some means that we don't know. We don't know. So we have no idea. And we are actually, some of these question marks I know that should be updated, but this is an old table of.
But there's no falsification. Does it mean that it could be just equivalent?
It's very hard to prove that some theory satisfies some principle. It's not something that you can do in a. It needs a paper, at least, or it needs a lot of work. Sometimes it's easy, sometimes it's trivial, sometimes it's not. For example, it was not trivial at all that no information without disturbance does not hold only for classical system. So if you have a theory which is non-classical, the system, because you can build up strange theories that are, they have classical system, but the composition of the system is non-classical. And you get systems that are not classical. So it is not something that you can, these are difficult proofs. Also, you don't have when you make a statement in quantum theory, you can understand in a very easy way things that are very complicated, like, for example, causality. Causality has been the birth of quantum information, because if you think the original paper about the possibility of try to remember the name of the author, it's very famous, Okay, now I will remember the name of the author soon. So there was an attempt to make superluminal communication. Nick Herbert wrote a famous paper with proposing a scheme for communication, instantaneous communication, by using stimulated laser emission to produce for each incoming photon with, let's say, eliciting up, get 2 copies of the up, and then get as many copies as you want by duplication by stimulated laser emission. And then if it's left, to get many copies of left, if it's right, it's many copies of right, and if it's down, many copies. So it was proposing a cloning scheme. And then using the cloning, it was saying, we share an entangled state. If Alice performs a vertical measurements, Bob has a vertical state, right? If Alice performs a horizontal, then Bob has an horizontal. Now, Bob cannot know the state, but if he makes many copies by this way, he can get the state, and then he knows which direction Alice uses, and this makes visible a communication, right? Unfortunately, the reviewers of this paper were, I don't know, I remember 30 reviewers, something like that, didn't have a way to prove that it was wrong. Apart from Ghirardi, who wrote a proof of the no cloning theorem, which didn't prove that it was wrong, because the fact that you cannot clone perfectly does not mean that you cannot clone approximately and make a communication with errors and then correct the errors by Shannon techniques, which makes you need to prove that the probability of or error is exactly 1/2, because this is 1/2 plus or minus an epsilon by sufficient redundancy, and you can make perfect communication. So the point is that Nick Herbert needed the causality theorem to prove it, and by causality theorem is the equivalence of 2 diagrams. You prove it in a shot, but in those years there was not the notion of causality in classical theory. So to me, it becomes important to understand by reasoning, not just by calculations, because the calculation of the laser case was horribly difficult. In fact, it was done by Nicolas Gisin. And it comes out that the few photons that you get from spontaneous emission spoils everything, which is very hard to tell. So the calculation does not mean to understand. Conceptual understand is another thing. And this is why we consider the OPT and this logical framework so important, for having a conceptual understanding in addition to the one from calculation. Other questions? Sorry, I'm talking too much.
No, it's fine. So I'm gonna read the list. Richard, then Maria, then there's me, but I can wait. Then there's Cyril, and then there's Alessandro and Patrice. So Richard, please.
Hi. So I suppose I've developed another question on the way, so perhaps I could insert myself later in the list as well, so I'm not just stealing all the time. But the question that's popped up relates to the axioms that you presented earlier. Purification, so on and so forth. Mm-hmm. Basically, with regards to like physical principles and physical laws having some sort of phenomenological meat. So I mean, take thermodynamics. You can sort of say things in a childish, but it's still in a way that contains like the heart of what's going on. Hot things get cold, things get messier. If you go to general relativity, you can't tell if you're falling or floating. Special relativity, speed of light is your maximum. Newton's laws, you kick it, it keeps going till it hits something. There's like a firm grounding. obviously your stuff is much better than a classical quantum theory, you know, with von Neumann's description, which is unrelated to reality. But is there, for each of your axioms, a sort of childish description that encapsulates basically what's going on, plus or minus some subtlety? But I've looked at your stuff before and tried to do that, and in some cases, causality is obvious, you know. But certain other things, purification, for example, but discriminability sort of makes sense, but I can't get the same sort of clear statement in my mind, and I don't know whether you can offer one.
Let me restate your question to understand if I understood. So you are saying, is there a way to understand everything in terms of this kind of reasoning instead of using Hilbert spaces? This is what you...
I suppose it's less mathematical than that. It's more,
more conceptual.
In your mind, is there a sort of core description for each of your axioms that is very easy to understand, very physical, very phenomenological?
The problem is that I'm saying it takes years to understand all the logical consequence of logical assertions sometime. Because, for example, I formulate in very precise words the 6 postulates. And you understand the conceptual meaning of each one. But to prove the independence of postulates, and this is the case, for example, of geometry or, you know, mathematics, it's an undecidable problem usually. So the point is that the only way to understand is to build up a lot of conceptual assertions, and then to be able to understand in terms of this conceptual assumption. You need to build up a lot of new notion and new conceptual. And for example, the local discriminability by itself, there is a very long paper written by Hardy and by Lucien Hardy and another person I don't remember, which is devoted to the local discriminability postulates. It is so powerful, and going to bilocal, so the fact that you can reconcile the holism with the reductionist reductionist observation approach is something so new, because we need experience. You know, it's like in philosophy, no? You are discussing with notions that everybody can understand in principle, but then it takes centuries sometimes to understand trivial consequence of some assumptions. I don't know. I really don't know.
Very quickly, sorry, can I ask you again the reference on the local discriminability? Because I think I'm not the only one. I'm having troubles with this more than with anything else. Okay. So can you give me the reference?
Let me tell you. The reference is Hardy and Wouters. Yes, famous Wouters and Hardy. Wouters and Hardy. There are not so many papers written by both together. I think it's the only one, or one of the few one. Wouters and Hardy is a very long technical paper. And by the way, quotes our paper hundreds of times.
So we don't have much time. We have 17 minutes. So Maria?
Yeah, just again on this local discriminability, sorry. Because it seems to me that it's very crucial also, because it's the thing that the real quantum mechanics has not in common with.
Right.
And this, so my understanding of this principle is that you are saying that in principle is possible observe. I mean, I'm sorry, I'm converting it in more experimental.
Yeah.
I don't know if it is the case, but it's my understanding. So it's basically there is not in principle forbidden to, in your theory, to infer the existence of a global process onto systems by observing just the single systems. Is this the thing? So yes. You can do local observation and you can still infer that they are correlated by a global process which involves both?
Yes, so I understand your question. So if you have the real quantum theory instead of the usual, you want to know what is a state of which is entangled, right? You cannot do this by performing measurements on A and B. What you need, you need two systems. You need a joint measurement, which is like, for example, a Bell measurements or interaction between two systems, which makes a measurement. So you need to make them interact. Yeah. So otherwise, without interaction, by just local observation, you can end classical communication, LOCC.
Yes,
you cannot do by LOCC.
Exactly. So I want to understand if this principle that you put in your theory goes beyond this, in the sense that it in principle allows more than this, or it is just so I mean, it's quantum mechanics. In quantum mechanics, you cannot do it. Yeah, this we agree. But so it is this principle is stronger. Is it in principle allowing something more, or is just saying this in formal?
No, I'm saying if you go to real quantum theory, is weaker.
Yeah, exactly. So you're saying that in real quantum physics, it is not possible to.
Yeah, but this is also true. Also, for example, for fermionic quantum theory, does not hold. But these are pretty good theory, because it's something that you can, it allows you to make observation. It's a little bit more complicated. Suppose that you want to observe one system which is on Earth and the other which is on a very far distant star, and they are entangled. You cannot do it by classical communication between Alice and Bob with the two systems. So it's a limitation to knowability, but it's not such a huge limitation. It's a limitation.
Yeah, but so it means that there exists an experimental. That is possible to think some experimental proof of the fact that, I mean, if there is no such a system. So
from the experimental point of view, is that you can do tomography of one system, of two systems, or three systems, by just making tomography of a single system. We're making many tomography of a single system. So you can reconstruct an entangled state and tell which state is that by making tomography on A and B. Usually two single tomography apparatus on A, one on A and one on B. This is the only thing you. So it's a simplification, practical, but it's not such a strong motivation, because you can make it interact. The point is that if they are very far apart, the interaction is very costly, whereas the classical communication is very cheap.
Okay. Okay.
So it's an economical epistemological postulate.
Okay. Okay. Okay.
No, the one that are less economical are causality, atomicity of composition. These are, or perfect discriminability, compressibility. These are less. They are more crucial, and also purification in a sense, because you can certify a probability. For example, this is something you cannot do in classical theory, apart from apart from nothing, because either how can you generate a random number which is really random with classical information theory? You cannot do that.
Yeah.
So
I would like to comment on that. I guess I'm a bit confused, because you can do local measurements to reconstruct a bipartite state. No, is that quantum state tomography?
Yes,
that people
exactly.
do. I guess maybe there is a hypothesis behind that at least I didn't hear. That is, you cannot know the bipartite state if you choose a single observable, because if you choose different local observables,
Yeah.
You can do state tomography. So
yeah, but you can do state tomography by choosing local observables only if it satisfies the local discriminability postulates. Otherwise, you cannot. So if you take a fermionic theory, for example, or real quantum theory, you cannot do that. You need an apparatus which is a Bell measurements, something like that, which is entangled. Measuring apparatus, it must be entangled. You cannot do without entanglement in the apparatus.
when you mean real quantum theory, you mean standard quantum theory, is that it?
No. Real quantum theory, sorry, is sorry. Real quantum theory means instead of being on the complex field,
Okay.
the space is on the real.
Okay.
I'm sorry. Oh, I thought
okay.
that, yes.
No, okay. I didn't know the term, but okay.
I'm very sorry. I should have said that, but I am living in a community where everybody says real quantum theory in this sense.
Sure, no problem.
So, so we have, I think we can have like a 10-15 minutes therapy session on realism. First, there is a very short, I hope it's short, please keep it short, question from Alessandro on, yeah, like if you can both ask and reply quickly so that we move to realism.
Yeah, it's a very simple yes or no question. So the question is there any way to derive a good axiomatic of, I mean, did you try or anyone try to derive a good axiomatic of open quantum systems?
No, but this is, okay, I like your question. The theory that we derive is already the open quantum system, because the notion of, okay, let me go to, I have some transparencies for this. Let's see. Nope. Okay. No purification ontology. There are no paradox. There is the difference between open quantum system and closed systems is only historical and comes from the fact that the original translation was always with pure states. And then I'm saying von Neumann himself devised the notion of a density operator, but in the framework, the notion of state is a vector in the Hilbert space, is not a density operator, right, in the axiomatization. Here, we start with the notion of state, which is totally independent on the notion of Hilbert space. So, and we arrive to let's see, I want to show another transparency, if I can find immediately. So when we derive quantum theory, we derive quantum theory of open system already, is already that, because that's the quantum theory. Everything else is what I call an angel, something that is not needed logically. It is logically coherent, is beautiful, but is not needed. So the fact that the transformations can be obtained, maybe we can start from this. Oh, okay, sorry. The fact that the transformation can be obtained by unitary, like here, for example, we have a channel, what is called a quantum channel, is a deterministic transformation, can be obtained by a unitary transformation, by suitable preparation of an environment, and by discarding the environment. The fact that you can obtain every probabilistic transformation in this way, for example, by unitary and von Neumann, does not mean that this unitary actually exists. This is what we think all the time. This is wrong, because we cannot falsify the fact that there is really a unitary going on. So we say the transformation in quantum theory are unitary. That's not right. The transformation in quantum theory are probabilistic, generally. The difference between closed system and open systems is only academical, because what we see is always probabilistic. We never see unitary transformation. Sometimes we can rebuild up by tomography, the unitary transformation, and it is actually unitary. But it's not. But we needed to perform many measurements on the same transformation, on the system prepared the same way all the time. We cannot do it if we don't know which is the environment. Most of the time, when we have a probabilistic transformation, we say, oh, this has been done by a unitary, like, for example, in particle physics. And because we know it's unitary, but we cannot falsify if there is really another system because which is interacting unitary with our particle, because we don't know where it is. We don't know how it interacts. We don't know. There are infinitely many unitary which give the same transformation. There are infinitely many systems which give the same transformation. Why should be the one that I want? Okay, one can say it's field theory. That's not true. Even field theory does not say that. And because there are the so-called ghosts of Faddeev and Popov. So the fact that when you build up a unitary transformation in quantum field theory, this is what is a Feynman path integral. By the way, it's not defined. Anyway, apart from that, you have to fix the gauge. And in order to fix the gauge in non-abelian gauge theories, you need to introduce the ghosts of Faddeev and Popov. So you need to introduce some entity which cannot be falsified anyway. And indeed, I'm not the only one who says that there is no need of unitary, because there was the famous problem of the black hole, the information paradox, right? The information paradox comes from the fact that we suppose that every transformation is unitary. But there are many people who say, why it must be unitary? There is no need of every transformation must be unitary.
Sure.
So the point is that this is what I call the angel of a theory. So is an element of the theory which can achieve elements of the theory and is very powerful. Like unitary is a symmetry, so it's powerful in this sense. And is logically coherent within the theory, so it's beautiful, it's powerful, it's logically coherent, but it's not falsifiable. Because we don't know interaction with what. We don't know with what. We don't know which interaction. And is not necessary for completeness of the theory. So the theory is just what I showed you before. And by the way, this means that all paradox in quantum theory are not paradox if you formulate the right quantum theory. The right quantum theory is the one that I showed you before. Where is it? I try to be organized, but it's never.
Sorry if I jump in, but I'm afraid that saying that there are no paradoxes 5 minutes before the end of the discussion.
Sure. You can ask.
So yeah, so I think Cyril had a question on realism, and I think many people want to hear at least something more about that. So please, Cyril, if you wanna.
Okay, yeah, so that question will be very quick. I'm not sure about the answer. The question is on one of the slides about the theoretical motivations. I think you had written that we could or we should abandon realism.
Yeah.
So the question is whether we should or we could, or do you take it as a very strong statement that there is no realism, or that you can just get rid of it or do without it?
And maybe what do you mean by realism also?
We should and we can. We should because we need to have a theory where there is a difference, very clear cut between what is the objective datum and what is the theoretical notion. So in the OPT framework, the objective datum is the event which happens and which we describe by normal language, and which we make formal, mathematically formal also. And this is which events occur is the objective datum, and why it occurs is the theoretical thing. So we connect events each other by a theoretical notion. The particle, the system, the spin is a theoretical notion. We never see the particle. is just a theoretical notion. And actually, as a theoretical notion, is also not an object. So we cannot see it by definition, because we see only objects.
So would you go as far as saying that there is no reality?
No, no, there is. The reality is my experience of what I see. Is not that, is a supposition that there are objects outside. Because I'm saying, if I take this pen, this is empty space. It's made of atoms and molecules. So this is theory. But what I see is a pen. So I always confuse theory with what I see. This is why I should abandon realism.
Just a quick question then. So what the theory is about then?
The theory is about what I see, which is not that what I see must be done how the theory is. So it's this ontological jump. The fact that I want the word made as exactly as my theory says, which is not true, because the theory can be wrong, can be falsified. So then the word disappears. In fact, classical theory is wrong, and the word has not disappeared. It's still there.
So I just to clarify. So I understand why you talk. So until you talk about why we have to get rid of objects, and there is the Malaman theorem that there are reasons to get rid of objects, and I follow you up until that point. But then I don't understand why the jump from realism, also after the reply you just gave to Cyril and Vincent. So if by realism we mean there are objects and we put a lot of requirements over how objects need to behave, they must be localized or whatever, then yeah, probably we should be anti-realist, or it's likely that we should be anti-realist. But I don't understand why, like a field ontology, it's not a form of realism to you. I don't understand why.
No, the point is that when, so we want to distinguish what is theory and what is what we see. So the field is something that we cannot see. By definition, is a theoretical notion. So is an objective in some sense, because it has, like mathematical notions are objects. They have properties, they have, they can be composed. So the mereological and property connotation of the object can be true for many other things that are not stuff. But the point is that when I think reality made of stuff, that's the point. It's made of particles. I have to use my fantasy to do that. And by the way, if it's made of particles, it's mostly empty space, but still it looks stuff, right? But there is completely empty space in an atom, right? In an hydrogen atom, the nucleus is a small ping pong ball in a football field, right? So what does it mean? We still don't have the notion of what is the size. Really, is the size? There are different definitions of size in many sense. So we want to see the matter exactly the way in which we describe theoretically. Why? We don't see anything.
I guess I'm not trying to say this. I'm trying to say, well, there are many things we should reconceive about how we think about the stuff. Definitely, we should look at physics to reconceive what the real stuff is. But as far as I don't have a conclusive argument to the extent that there is no stuff, I should keep believing in stuff. And, you know, again, maybe stuff is not at all as I suppose it was. I'm happy with that. I mean, I might be less happy if I'm Bohemian, or I'm more happy if I'm something else. But still, I understand that. I don't understand where the jump is from.
No, okay.
No particles, no stuff.
If you want to believe in the ontology, in the metaphysical sense of the notion of field, because we say that the real thing which exists is the field.
But not because I want to, but because, you know, if you talk about like information support, for instance,
right?
Like in the box.
Yeah, the point is that it is something which is, we can believe that the field is actually there, if you want to believe that the field is actually there, but don't forget, it has no property. The field is just a bit, a set of bits that are not made of stuff. Is not stuff, the field. So it's really something different from stuff, because stuff is the state of the field. It's something that you dress the field with. Is by the way, is probability rule. So this is something which, you know, field theorists understand. I'm saying that, like, for example, Kuhlmann or many others, Malamente, not only those. Jeffrey Bull.
So would you say that stuff's made out of non-stuff things?
The most fundamental thing is not stuff, is the field, which is a support for states. And the support for states is an informational notion. Because what has a state? A bit as a state, a qubit as a state. What is a qubit if it's not a spin? A spin is stuff. But if I gave you a field, what is a field made of?
Sure, but could be the case that these elementary qubits are elementary stuff, no?
Yes, but these qubits they don't have properties. They have states which give properties, but they don't have. Is not a bit. Is not hardware. The bit. So this is actually the way. If you want to be faithful with the field theory, you have to think in this way, because the field exists and the field has states and the particle has states of the field. And this is what the elementary quantum field theory says. There is no need of being an expert.
Yeah, but quantum field says nothing that the field is not a stuff. No, that looks like a choice to me. The quantum field theory, usually standard quantum field theory, doesn't say anything that the quantum fields are not stuff. It's just that the particles that we are used to think of stuff are not the fundamental object. But that doesn't mean the field is not stuff, or it is not made of another stuff.
Yeah. So this is what I see are particles. This is a probability rule. This is what quantum field theory says. Because what is a particle? What is a particle? It's not a ball, it's not a marble, it's a probability rule. And this is serious because usually we see localized particle by effects on detectors. Come on, the last particle we have seen, the Higgs boson, is the result of the analysis of a huge set of observations. We have not seen it. No, this is not just a joke. The point is that we want to believe that the particle is like the marble that we have in classical physics all the time, but it's a probability rule. What does it mean? I'm saying, for example, there is this work by Berto about the indistinguishability of particles and the self-identity. All his assertions are meaningless if you think that the particle is not an object, because indistinguishability of particles is crucial. To use this word indistinguishability only if you think to particle with property to distinguish between them, because if you don't have properties, there is no issue about indistinguishability.
Well, I guess, sorry if I can very quickly. So on behalf of Franz, I think what he's saying is that indistinguishability by itself does not imply lack of individuality, which I think, so that's a point that I believe is independent from quantum mechanics. So if you believe that identity is defined via Leibniz law, both sides of Leibniz law, then indistinguishable particle would imply failure of identity condition. And that's, again, that's independent from quantum field theory, from quantum gravity, from everything. If that's the case, then there is no identity. And what he's saying is, well, there are many ways to give identity, to define identity that do not use Leibniz law. And before, giving up identity, we should, consider those other primitive identity. It gives name, echeitism or whatever. But I think so that's independent from quantum field theory. You can bracket the issue of quantum field theory from Fran's discussion. But I also had like a very small.
Yes.
I mean, it's not small, but like. So I guess I'm not sure we've been talking about that for like 5 years. So I'm not sure we will ever agree on realism. What I want to see is whether, the motivations you have for your framework seem to be somehow based on realism. But as far as I can see, they are still independent. So what I'm wondering is it possible to appreciate or to even, develop, pursue this framework, this approach to quantum theory, this derivation of quantum theory, without being committed to such a strong attitude, anti-realist attitude. So what I'm thinking is, I'm still realist, right? No. But I believe that what you're doing is very useful to make the theory clear. So do you think I'm wrong in thinking that there is this like independence between your framework and realism?
Christian, you are right. I am, the point is that when I presented this kind of result to a community at large of physicists, and this work has lasted more than 15 years now. So there are maybe 70 or maybe 100 of papers published. So it's pretty established. The point is that I find people that don't like the notion of doing physics with information. A lot of people don't like, they want to see stuff, not information. And so personally, I'm not against realism by definition, but I am against people that are not open to use this notion as a constructive notion for theories. And unfortunately, we didn't have the time. I am open to round 2, if you want, to see quantum field theory, because the point is that the way in which you build up quantum field theory by the algorithmic paradigm is extremely powerful. So you just take the easiest algorithm, quantum algorithm, and this gives you Weil, Dirac, and Maxwell. Then you have to build up from very simple starting point. You don't even use covariance. Relativistic covariance is a result of the construction. So information communication gives us relativity, special relativity, not general one, unfortunately, because if otherwise I would not be here to try to convince you. But special relativity is not assumed. And if I tell you why, you will laugh. Why relativity comes out? Very simple, because of discreteness. Because there is some time to go from one system to another, to have communication. In the continuum case, you have to assume it. In the discrete case, it's automatic. It takes some time to make a transformation.
Which I think was also sort of the question Patrice wanted to ask. So I'm very sorry we have to stop here.
Yes.
We already squeezed you enough.
I just want to say that I'm ready for a round 2 as well.
I would be happy to. So I guess everyone would. Maybe we can chat later and see when we can do it. But well, let me thank you a lot. I think we should
You are You are
So thanks a
very
lot, Mauro.
kind. Thanks to you for listening to me.
And sorry for stealing the last time with a question. I should
Okay.
have.
Okay. Okay.
See you soon and take care. Stay safe, you all.
Yeah.
Thank you very
Bye.
much.
Yeah, thank
Bye.
you.
Thanks
Thank
to
you.
Thanks
Ciao.
to you. Very nice to meet you. Bye.
Bye.
Bye.